Section 4 of Chapter 3 is about direct variation. So by the end of this lesson, you should be able to write and graph direct variation problems, and then solve problems involving direct variation. So let's talk about what that is. Direct variation is described by an equation in the form y equals k times x. K cannot equal 0. So you can have absolutely any number there in the world besides 0. It can be positive, it can be negative, it can be a fraction, it can be a decimal, it can be a whole number. This equation illustrates a constant rate of change. So in the rates of change that we talked about before, this number that you find, right here, is your rate of change. This is also called the constant of variation or the constant of proportionality. So we need to name the constant of variation for each equation and then find the slope of the line that passes through each pair of points. So this first one here, if we look at the equation, remember your k is always whatever number is hanging out with x. So in this case, k is -4. Now if we find the slope, remember that slope is rise over run. We could plug it into the equation, or because we have a graph, we could just take a look at it. Rise over run. So if I start at this point, I'm going to go down 4 and over 1. So -4 over 1 is the same thing as -4. So if you notice, the constant of proportionality and the slope are the same. Let's double check to see if that works for the next one or if it was just a fluke. So here's our equation, y equals 1/2 x. Our k is the number next to x, which is 1/2. Now if we find slope, remember we do rise over run. So I rose up 3 and I ran over 1, 2, 3, 4, 5, 6. And if we do rise over run and simplify, 3, 6 is exactly the same thing as 1/2. So when you talk about this equation that you have right here, whatever your rate of change is going to be the slope on the graph. The slope of the graph is always that, like we just said. And since if you plug in 0, you get out 0, it always passes through the origin, or 0, 0. That means that your x and y intercepts are always 0. So like we did in 3.1, we graphed things with intercepts. It is not helpful to graph a direct variation equation with intercepts because that only gives you 1 point. So you know for every single one of these graphs, it has to go through 0, 0 because they're direct variation. Now if I want to find the rest of the graph, remember we need 2 points. So if I look here, the first thing I'm going to pick out is my constant of variation, which is 6. Remember, that's your slope as well. Slope is always a ratio of rise over run, which remember means that we need 2 numbers. We need some numbers to rise, and we need some numbers to run. So they just give me 6. Remember, I can turn that into a fraction, and 6 over 1 is the same thing. So to get to my next point, I'm going to go up 1, 2, 3, 4, 5, 6, and over 1. Remember, all you need is 2 points to make a line, so that is our line of y equals 6x. Now we can do the same thing with the next one. The next one's kind of cool because they gave our k to us in a fraction form. And remember, that's our slope, rise over run. So it starts at 0 because it's a direct variation equation, and then I'm going to rise up 2 and run over 1, 2, 3 to get to my next point. All we need is those 2 points, connect them, and we're done. Now the next one's a little different because it's a negative, but still find your k. It's -5. Remember, we want to turn it into rise over run, so we need a fraction. -5 over 1 tells me that I have to rise down, or go down 5 over 1. Make sure when you do this that you don't go backwards 1, that you go forwards 1. The way you can check that is if you originally went backwards 1, your line looked like this. This is incorrect. This is a negative number, which means that your slope should go negative. It should fall down. Same exact thing with this last one here. Your k is negative 3/4, which is rise over run. So I'm going to go down 1, 2, 3 over 1, 2, 3, 4. And then double check that it makes sense. My line goes down from left to right. This is negative. It makes sense. All direct variation equations share some common characteristics. This is the form they should all be in. They all go through the origin of 0, 0. If it's positive, they should move up, and if it's negative, they should move down as we read it left to right. So now let's do some algebra with it. Forget about the graphs. Suppose y varies directly as x. Y equals 72 when x equals 8. We need to write a direct variation equation that relates the two. So remember, all direct variation equations look like this. Y equals kx. We don't know k in this case. We need to find it. But what they do tell us is y equals 72 when x equals 8. So we can use our algebra skills to divide both sides by 8 and figure out that k has to be 9. That's our constant of variation. Like if we were to make a table of x and y, right now we only have one point. We have x and 72. But knowing this, that means that this has to go up 9 for every one that this goes up. So if this was 9, we'd add 9 here and we would end up with 81. And we could continue this table forever and ever. But once you find your k, all you got to do is plug it in. Y equals 9x is my direct variation equation that relates these two. So now we're going to use this to find x when y equals 63. So all I got to do is plug in 63, use some algebra, and we end up with x has to be 7. So if we wanted to make a table, 63 and 7 would be there as well. Let's do a story. The distance a jet travels varies directly as the number of hours it flies. A jet traveled 3,420 miles in 6 hours. Write a direct variation equation for the distance flown in time t. So remember, it's y equals kx, but they changed this into distance and time. So we could write it like this, d equals kt. And then plug in what you know. I know the total distance it traveled was 3,420. We're looking for k, and it did it in 6 hours. So if we use our algebra, we can find k, throw this in our calculator, we end up with 570. So our equation is d equals 570t. Now if we go to graph this, remember we have 1.00 because it varies directly. And then we have another point right here, miles and hours. So our independent variable is going to go down here. 1, 2, 3, 4, 5, 6. And then it went 3,420 miles. So let's count by 500s. 1,000, 2,000, 3,000, 4,000. So this point would be about 6 hours, somewhere right around here. And now that we have those 2 points, connect the dots, it goes on forever and ever. Then they ask us to estimate how many hours it will take to fly 6,500 miles. So let's extend this. So 6,500 would be right in the middle of that 6,000 and 7,000. Come over here, estimate, draw this down. This is 6, 7, 8, 9, 10, 11. So I'd say like 11.8-ish. And we can double check our math by plugging it in. So remember, we have this formula. I want it to fly a distance of 6,500. So all I got to do is divide both sides by 570. if you do 6,500 divided by 570, I got 11.4 for time. So my estimation was a little off, but maybe it's because this graph or this line wasn't very straight, or maybe this obviously is not very straight as I come down. But we got close enough that I can say that my graph did a pretty good job. So you have a few to try on your own. This is like the second to last problem we did, and this is like the last problem we did. Make sure you write down any questions you have, and we can go over them in class. Enjoy your night.